All right, so in this video lesson, we are going to study how we can find tangent planes. It's a method that we can find tangent planes for any multivariable function. And then as an application of that, once we've learned the method of how to find a tangent plane on a surface, we're going to apply that into finding the linear approximation of a function at a given point. Okay, and so this particular method here, this particular study here, we're going to have to focus particularly on a function of two variables right here. Okay, because we cannot really find, but then we can easily extend that to function of three variables and further. But for function of three variables and higher, we cannot draw a graph, and we don't really have a graph existing for that. And so that's why most of my pretty much all of my explanation is focused on a function of two variables. Okay. All right, so now in order to understand the method of how we can find the equation of the plane tangent to a point given on the surface, then let me bring up a surface as following. Let's say we have a function that's given, a function of two variables, as I said. And this function has a graph being a surface. And for whatever function that is, being two variable, it has a graph being a surface here. So let's say we pick a point. And so now that point on the x and y floor it has coordinates a comma b. And then that point right here, the height where it creates. So at this point right here, a comma b, when we when we substitute this point into the function, then it becomes a point sitting on the surface, like everybody knows that at this point. And so that point right here is specifically a comma b comma the function's output value being, or we can think of that as a z value right here. This is the z value. Okay, and so the idea now is that, think about, hey, if we're at that point on the surface and we would like to find a tangent point, we would like to find a tangent plane. And so the tangent plane, needless to say, must be tangent to the surface at that given point. And so that's why this point here is also regarded as tangent point. We want to find a tangent point that's tangent to the surface at that point. Okay, so in the way how the picture is drawn, then believe me or not, but at this point you have learned all of that essential tools in order for you to find the equation of the tangent plane. So the tangent plane is a plane, and right here through that point we have the plane like this. And in 3D drawing, forgive me that I cannot make the best picture out there. Okay, but it's some kind of point. That's the idea. Okay, and so the tools I talked about, that I mentioned just now, that everybody has already learned, and the method to find the tools here, those tools are essentially just partial derivatives. Because the idea now is that right at that tangent point, there you have seen this idea before. There's a tracing curve along the y-axis, and so there has to be a tangent line along the y-axis, and there will also be a tracing curve along the x-axis. This is what that curve is all about. And on that curve containing the tangent point, we will be able to find a tangent line right here. Okay, a tangent line along the x-axis. And now the two tangent lines now, and so now think about the tools I was talking about, the tools that get us there in order to find the equation of the tangent plane. The tools there is partial derivative in respect to x and partial derivative in respect to y. This tangent line on the tracing curve along the x-axis can be found by the partial derivative in respect to x, and this tangent line right here on the tracing curve along the y-axis can be found by finding the partial derivative in respect to y. Okay, and so now if you notice on my picture, when I drew the two tangent lines, when I do the two tangent lines, I purposely put arrows on them. So indicating once we found the tangent lines, we will treat the two tangent lines here as some two vectors. So the idea now is that the plane here the plane that we're about to find, the equation of the plane that we're about to find, the plane itself has to contain that tangent point and must also contain the two tangent vectors here, or in other words, these two tangent vectors that we can find through the f of x and f of y here must be sitting or must be contained right on our tangent plane. And that's the idea right there. All right, so before we get any further, I'm not going to get directly into just write down here's the method. That's going to be a little bit too extreme in terms of taking out all of the details. So let me now, I'm going to leave the picture here. I'm going to swing to the other board. I'm going to bring up a demonstration example problem right there. And then I'm going to switch back and forth between the two. The plan now is that I'm going to work through an actual specific example. And then along the way, I should be able to recognize and point out a generality on this side of the board again. Okay. So just think about that surface. Let me now start out with the example. How about we're given a function as following: f of x comma y equals 1 minus x squared minus y squared. Okay, and the goal here, yes, we want to find the tangent plane. I'm running short of board space here, so allow me not to write down the goal here. We want the equation of the tangent plane. Okay, we want equation of tangent plane, but formally speaking, find the equation of the tangent plane at so now let's say the given point here is 2, 1. Okay, the tangent, this point right here is that point sitting right on the floor. So let me one more time swing back to this side of the board. See, 2, 1 is this point on the floor. And so now 2, 1, that's given in the specific problem right here. You can think of this surface here as the surface, even though it may not be the exact accurate version of that. But this surface represents the surface of that graph. It could be. Okay, so 2, 1 is, you know, when we put that on the surface itself, it's that point 2, 1, comma, the z value that which came out from the output of our specific function. So let's quickly find out our tangent point value. Okay, so tangent point value here we have z equals f of 2, 1. Okay, and so this step right here, in this video lesson I'm doing it right now, but when you're actually on your own and fluent enough with the idea, that you can really put the step a little bit later. So f of 2, 1, the function value, the function evaluated at these two. And so that's going to give me 1 minus 2 squared minus 1r squared, and that gives me a minus 4. So tangent point here really is the tangent point, and I will come back to dive in a little further, but tangent point we have really is 2, 1, negative 4. So this is the point that's being on that surface, the point on that surface, and this is the point where the tangent point is tangential to the surface right at that point on the surface. Okay, this is just about the location on the x and y floor, but this is really where the plane is tangent to the surface, on the surface itself. That's why I call it as a tangent point, and in short writing it's T point. Okay, so let's put that there for now. On my board, I was indicating, and according to the drawing again, with some brief explanations I've given earlier, the idea now is that right at that tangent point, there has to be two tangent lines. One tangent line is being along the x-axis, and one tangent line being along the y-axis. And of course, we're going to have to find those two tangent lines by going through the work of finding f of x and f of y. Okay, so that means, needless to say, we're going to have to, in my next step for the specific example, I am going to find these two partial derivatives. So partial derivative in respect to x for our specific example here. And so at this point, anyone viewing this lesson here must be fluent with your skill in finding partial derivative. So I hope I can speed up the process here, but partial derivative in respect to x for this function is a minus 2x. Minus 2x. The partial derivative in respect to y for this function is minus 2y. It's minus 2y. Okay? And so now we don't, so this is the general expression representing the slope of the tangent line on that tracing curve. Okay? So that means we're now going to have to substitute it. So f sub x at 2, 1 will be, so I'm going to take this pair value, substitute that into my f sub x. That gives me minus 2 times 2 for x, that's minus 4. Okay, and I'm going to also calculate f sub y at 2, 1, which gives me minus 2 times 1. Okay, which is a negative 2. All right, so this is the important part for anyone to understand, but this is only the slope of the tangent line, right, along the x-axis, on that tracing curve along the x-axis. And I'm actually somehow glad that I drew a picture that's consistent enough. I'm not saying that it's the exact graph, the exact surface of this particular function, but on the x-axis, this tangent line has negative slope, and so along the x-axis, at that particular point, this tangent line is at negative 4, slope negative 4. Okay, the slope is negative 4 for that. All right, or as thinking of that in terms of an instantaneous rate of change right at that instant, right? This line or this tangent line is falling in a rate of minus 4, vertically minus 4 over one run into the positive x-axis, over one run to the positive x-axis. Okay, and then the y, now right on that tangent point, think about you freeze yourself to this surface, to this cross surface right here, parallel to the x-axis. Then the y value on that, because now I want to lead everybody into thinking of this as a vector over here. This vector drops down by 4 in every one change in the x direction, but the y direction is a 0. Okay, and so right from this, we don't need to get the complete tangent line here, but right here it's indicating for me that that tangent line is parallel to the vector v, to a vector v being, okay, we change 1, like I said, this here is a slope of the slope of the tangent line, the rate of change, it falls 1 over a 1 run in x. That's why I purposely chose, right out from that meaning, I purposely chose x equals 1. The y value equals 0 for this vector, okay, because it's right on the plane that's parallel to the x-axis. That means all y values can be defaulted. The y value can be defaulted to be 0. And then the z here, the z I explained earlier with the picture, the z value falls by 4 units. That's why it's negative 4 here. So negative 4 over 1. Okay? And so we have a vector that aligns with the tangent line along the x-axis. Okay? And so now similarly, I'm going to do the other thing right here, the other vector. So now with this value right here, I'm looking at another vector w. Okay, this is the slope of the tangent line along the y-axis. Minus 2 is the slope of the tangent line along the y-axis. And so in that similar argument, okay, now along the y-axis, then that means we're gonna set the x value for that vector to be 0. Okay, because again, think about this vector right here. Okay, it's not going anywhere in the x direction. It's only pointing right along with the y-axis. And so we have some change in y, and we have some change in z, up and down, and on the y direction, but nothing on the x direction. Okay, and so that's why we have 0. We purposely set 0 for x. We set 1 for y, because by default, we understand any of these rates here, rates as how much falls or rise per 1 unit of change in y or change in x per 1 unit. And so it's easy enough to always set these two values, x or y, at 1. Okay, and then now the z here is minus 2. All right, and so now I have seen some generality already. So after getting the two partial derivatives, we need to substitute the actual point, the actual pair of value a comma b here, right, into the two partial derivatives, so that we can find, and then from there we're gonna go ahead and put that into the vector form of the two tangent lines. We get right into the vector forms of the two tangent lines. Okay, so in other words, the two tangent lines are parallel to these two vectors. Okay. So as a generality, after getting these, I am going to substitute the pair of value a comma b into our partial derivative. I am also doing the same for my partial derivative in respect to y. We get that. Okay, and then we're going to create the two vectors. So I'm going to call that one vector v being 1, 0. See, always 1, 0, comma the output value for partial derivative at a comma b. Okay, and then we can call that another vector w being the vector that aligns with the partial with the tangent line on the y-axis. Okay, along that tracing curve there. So it's going to be this time 0, 1, f sub y at a comma b. So we drew out these two generalities right here, right from the step that we were working with. Okay, and I put in hopefully enough detailed explanations earlier. All right. And so now we have the two vectors that align with our tangent, that aligns with our two tangent lines right there. Okay, and now as I explained earlier, and on the picture, the two vectors there need to be on the plane. Okay, the two vectors there need to be on the plane, and then of course the tangent point is there on the plane itself. And so now we have to bring back our understanding about how we find the equation of a tangent plane in general. So anytime we find the equation of a tangent plane, we need to know a point that locates the point, and then we need to know the normal vector indicating where the plane is facing. That's the way how I tend to explain to my students. We need to find a point that locates the point, and then we need to find a normal vector indicating where the plane is facing. Either it's facing that way, or facing this way, or facing that way. Normal vector. Okay, but now, so right now we haven't found a normal vector for our desired tangent plane yet, but we already knew that these two tangent vectors right here are contained completely on that tangent plane that we're about to find. All right, so now bringing back some learning experience we've had throughout those days, we were just specifically focused on finding equations of plane and equations of planes like that. Then the next step I'm doing, after realizing that these two vectors are completely contained on the plane like that, I am going to, and of course I'm going to have to erase out some space right here. And I'm going to rewrite my two vectors here. All right, so with the two vectors here, finding the normal vector is just a matter of, the normal vector as vector n is just a matter of taking the cross product between v and w, because cross product will be, now again, if these two vectors are both on the plane, okay, there's vector v, there's vector u maybe, I mean v and w, then the normal vector will be perpendicular to all vectors on that plane. This concept is already learned throughout the days that we were learning about how to find equations of a plane. So allow me not to get too far back into this. Okay, but now that is the reason why I'm taking the cross product between the two vectors here that are now known to be on the plane. And so taking the cross product, your skill in how to find a cross product need to be brought back in here. Okay, and the easiest way, I'm going to set up that determinant ijk here. Okay, the first vector v with coordinates 1, 0, negative 4, and then 0, 1, minus 2 for w. Okay, and then we can easily expand this out as a subdeterminant 0, minus 4, 1, minus 2, that with the I components, and then minus. And then once again, if you're feeling a little shaky with what I'm doing here, review your skills, review my lessons about how we find cross products. Okay, and then here we're looking at 1 minus 4, 0 minus 2, j, and then the last component here is going to be plus, and then the sub matrix 1, 0, 0, 1 is a determinant actually. Okay, and I, j, and k. Okay, so that means following your calculation, we're going to end up with the final vector as following. Okay, so that gives me positive 4. Okay, the middle component here is going to give me positive 2, and the last component here is a 1. Okay, that's my normal vector. Okay, so this normal vector now is found. So some generality can be found here. Some generality can be recognized through the step I'm currently at right now. So after recognizing the two vectors that align with our tangent lines, our two tangent lines, right at the tangent point, then we're going to go ahead and find the normal vector of the tangent plane. That's the generality by taking the cross product. And then yes, it's always best to take the cross product by setting up this determinant. So I'm going to write down that generality right here. The normal vector as a highlighted step can be found by doing the v cross w, which is done by setting up, what can be easily done by setting up the ijk determinant. Where we're looking at 1, 0, this value right here is f sub x at a comma b. And 0, 1, f sub y at a comma b. All right, that's how we're setting up that determinant. And then how we calculate that determinant, it shouldn't be too important. But now, we can also draw out some important results here as well. You see, this 4 right here, okay, and sadly I erased that already, but you see this 4 right here is the opposite of that 4 right there is the opposite of f sub x at a comma b right here. This is really f sub x at a comma b. For our particular problem, this minus 4 was f sub x, the partial derivative in respect to x at 2 comma 1. But this is the opposite sign. All right, and this 2 right here, observe that it's also the opposite sign of minus 2. Now minus 2 was what? Minus 2 was the partial derivative in respect to y along the y-axis at 2 comma 1. And so this normal component here has the y components being the opposite of that f sub x, f sub y, a comma b right there. Okay, and then 1 here is always going to be a 1. All right, so now that is the generality that think about when you're actually working through your determinants here to find your matrix. Yes, you can easily come to something like this. So it now sort of becomes a formula. Okay, you're looking at minus f of x at a comma b, and then the middle component here is minus f sub y at a comma b, and then comma 1. That is, ladies and gentlemen, that is generally the vector, the normal vector of your tangent plane can generally be found like that. Okay. All right, and then later on I'm going to keep erasing some of the work here to make some more space to move on to the next step like that as well. Okay. And so we're close. We're very close. Now I'm going to erase some of the work here, and I'm going to need to retain that normal vector and the tangent point. All right. And so back to what I said earlier about the tangent point. See, after you find the normal vector, you can also find the tangent point at this step right here after you find the normal vector. So I found the tangent point, I put in the tangent point much earlier, but when you're fluent enough, you can decide to put the tangent point about right after you have found the normal vector. That works too. Okay, and so now we already had the tangent point, and our normal vector in this case was found being 4, 2, 1. Okay, so now this tangent point is contained on the plane, and we already have the normal vector of the plane. So now everything is ready for us. The standard method of coming up with the equation of a plane, of a 3D plane. Now, not only just a tangent plane, whatever plane is a plane is linear plane in 3D space. So the way to find that, okay, normal vector has the x component of normal vector has the component 4 over here. I'm going to multiply with x minus 2. This x minus 2, this 2 here came from the tangent point which is contained on a plane. And again, we've learned all of this. We should be fluent with this. Back from those days, we've been learning about how to find equation of a plane. Okay, so now I'm going to speed up the process a little bit. I'm going to add. So now I'm looking at 2, which is this component right here, this value right here, times y minus 1. Okay, this is the y value of the tangent point, okay, or the point that's locating the plane. And then I'm going to look at plus, and now it's going to be 1, okay, times z minus negative 4, which is now a plus 4, okay, equals 0. All right, ladies and gentlemen, as far as finding the equation of the plane right here, we're done. As far as finding the equation of the plane, of the tangent plane, we're done. However, now we are a lot further into our learning. So I want to specifically do something to this equation. As I said, as far as getting the equation of the tangent plane, we're done. But I'm going to purposely do the following. These are going to be kept the same, but I'm going to go ahead and distribute out a z right here. So this equation, I'm going to rearrange that as following. 4 times x minus 2 plus 2 times y minus 1. Okay, and then I'm going to have that. It's going to be equals to plus 4 equals minus z. So I distributed out the 1 to common factor to each term here, and then I'm going to subtract z to the opposite side. My plan here is to express z here as a final function. So even though it's a plane, I want to now purposely rewrite the equation of plane as a function in terms of x and y as a function of 2 variables. All right, and that's why I did that. I brought the z over. But now this is currently minus z. So one more step. I'm going to divide both sides by a negative sign and allow me to switch the equation, turn the equation around a little bit, meaning z on the left and everything else is on the right, because I'm more comfortable that way. So now it's going to become z equals, okay, minus 4. Okay, minus 4 times x minus 2. So it's just the algebra right after that important step. Minus 2 times y minus 1. Minus 4. All right. So now let's observe this. This minus 4 now is exactly the slope value for our partial derivative in respect to x right here at 2, 1. This minus 2 is exactly the slope value for our partial derivative in respect to y right here at 2, 1. Okay, the slope of the tangent line along the tracing curve along the y-axis. And this value right here, okay, this value right here is the z value of the tangent point right there. All right, I point this out because, and this is, by the way, the final form that we want to arrive at and be happy with that. Okay, but the generality I want to point out here is that, so at the end, this is the method, but if you would like to remember as a formula, then now you can do the following. And at this point, I'm erasing all of this work. That means whatever I'm about to write, it's the final step after working through the determinants and finding the normal vectors and all that. But your final tangent plane can just simply be concluded as following, if you are willing to remember this. it's going to be f sub x at a comma b. That's a value equivalent to the -4 from my equation on the other side of the board, times x minus a. Okay, this is the value a right from that. Okay, plus the partial derivative value at a comma b again. That's why we had a -2 there, times y minus b. Okay, all right, and then we're going to add with the function value at a comma b, and this was the reason why I had that -4, okay, on my other board right there, my other side of the board. So this is one quick fast formula in case you don't want to go through the whole method. Then you can remember this formula right here, and that is the formula to get the equation of the tangent plane at any given tangent point, okay, on a point. And that's about at the end of how we find that at the end of the method right there. And that's how simple that is, how easy that is. Okay, it took me some explanations, but when you're actually now sitting down and doing that on yourself, getting this is easy, getting that is easy, and then use this formula, substitute it in. That's how we're getting that. Okay, otherwise, if you refuse to remember the formula, yes, go through the process that I was explaining earlier. Okay. All right, and so right after we have learned how to find the equation of a tangent plane, that is, we can apply that into some important application here. Okay, and that application I'm about to introduce here is the application where we utilize a linear approximation. Linear approximation. Okay, so linear approximation always comes right after we've learned how to come up with the equation of a tangent plane. Okay, and so a plane, a tangent plane, a plane on its own in space is a linear thing because everything is flat out. Maybe it's pointing in different orientation, it's facing in different ways, but in the end it's a linear thing. It's completely flat out. It contains a whole bunch of line, turning in different direction. That's all. Okay, so that's why. So now the idea of linear approximation is as following. Okay, you have a function f of x. You're starting out with a function f of x, and that function f of x has some graph being some kind of surface. Okay, and so the idea now is that we want to evaluate. Okay, at a given point, a comma b right here. We want to evaluate this particular function's output, f at a comma b. We want to evaluate that. However, this work right here, a direct computation may be challenging. Okay, may be challenging. So we come up with the idea, hey, this point may be locally near. I'm using the word locally near, meaning maybe it's, and for anyone learning this lesson right here, you don't have to be too hung up with my terms locally near, like how local is local. That's not really important point. You can wait until one day when you arrive at a more advanced course in math, and you will have a better explanation about what locally near means. But just think about, we pick a point near that. But this point here, think about this point here. If we substitute that into the function, we have a different point. But these 2 points are near each other. Now let me name it. How about this other point being locally near? Let's call that some x naught, y naught, x sub 0, y sub 0. And so substituting that into the function, yes, it's this point right here, y sub 0. But then, and it's easier to calculate. But then the idea now is that from this point right here, I am going to shoot out a tangent line. A tangent plane. So I'm going to find the equation of a tangent plane right through this x sub 0, y sub 0 point. Okay? And then treating the tangent plane, this tangent plane right here, once again, I'm going to treat that as some linear function, x, L of x comma y, which is the tangent plane. And that's the reason why when you were learning in my earlier lessons about, in earlier part of this lesson about how we find the tangent plane, I purposely put the equation of a tangent plane in a way that is expressed as a function of x and y. Okay, it's a linear function of x and y. Okay, and then we're gonna use once we come up with a tangent plane, we're gonna really we come back and say, hey, the value that we evaluate for the function output at a comma b right here can be approximated by this linear tangent plane right here. We're going to substitute that a comma b into the linear tangent plane. Okay, and when we're substituting that a comma b value into the linear tangent plane, it's going to be a lot easier because it's only coefficient multiplied with variable, coefficient multiplied with variable. That's the thing about the linear function. Any linear function is a linear combination between coefficients and value multiplying and adding up. So it's only involving multiplication and adding. Okay, and so that's the plan right there. And let me now quickly do a computer graphic demonstration. All right, so on my computer screen right here, see, this is some surface representing the given function f of x comma y. And this point right here is some point, right? At some point that a comma b right here. So a comma b is this point that I'm having on the floor right there, and we want to evaluate the height of that. But then this may be this point, the coordinates value may be somehow challenging to directly substitute that into our function f of x comma y to calculate. So we're gonna come up with another point that's, see, so now I'm going to call this point somehow locally near this target point. And then that point there on the x and y floor produces this point right on the surface. And this point right here is the point where I'm going to shoot out a tangent plane right here. So the tangent plane comes out like that. Okay, and so this tangent plane in purple is a tangent plane that tangential to this surface at this point B right here. Well, my software names that B right there. So now you can see that the idea, let me purposely rotate so we can have a better view. See, the output for this point that we want to calculate, the height for that point is close enough to the height of that tangent point. And that's why we think about, hey, if we can, and then if we directly substitute this value a comma b into the tangent plane itself, it's even closer. Okay, it's even close, pretty close like that. Okay, the distance is pretty small, and that's the idea of how we don't really calculate the exact value, the exact height from the floor up to the point, but we say that, hey, this height right here is approximately close to that height where we substitute this into the equation of the tangent plane. Okay, and that's what this approximation is all about. And so we are about to approximate this value but using a linear function. That's why it's called linear approximation. And then many textbook authors also refer to this, many other professors also refer to this as a process of linearization. Okay, you may hear about this term here and there throughout different textbooks, linearization. But linearization just means we find a linear approximation of a value, because instead of substituting that directly into the function, we use a linear function to the function that comes from the tangent line, equation of a tangent line, to approximate the value. All right, so now after all of the theoretical talk right here, let's get to it by doing one demonstration example. All right, so in this example here as a demonstration, and yes, I titled that an example. Let's say we are given a function f of x comma y equals x y squared. Okay, and so as I was describing earlier about the process right there, then needless to say, we need to definitely be able to find the equation of a tangent plane. Okay, the equation of a tangent plane. But let me complete the problem right here. We want to, for this problem, we want to estimate. Okay, we want to estimate or approximate. We estimate the function value here at 1.01 and 1.05. Okay. And so now before we get started, let me bring in the reason. the reason that we only want to estimate using a linear approximation, because here's the thing, if we directly substitute this, see right now in this notation right here, it means we substitute 1.01 into the function for x, 1.05 into the function for y. So we're going to end up with the calculation as following: 1.01 times 1.05 all squared. But performing this computation, oh boy, we do need to use a calculator. And of course, using the calculator is what we definitely need, but a calculation like this involves the powers and all that, right? Some basic calculators in these days still exist, in these days, don't have raising power operation, okay? And so that's the idea, that's the reason why we now don't want to go the direct route, substituting it. We want to do the following. So now I'm going to first come up with my linear tension point. And I apologize, I'm a little rushed here, but first of all, 1.01, 1.05 right here. I can easily recognize that this point here is near 1, 1. And this point, the reason I chose this point is it's close, it's easy for this calculation. It's easy for finding the tension line and all of that. So basically it's a lot easier than working directly with this point. And that's why, and this point here is quite close with that. Okay? And so now I'm going to use this point right here. I'm going to find a tangent plane at that point. So tangent plane at 1, 1. Let's find that. So prior to this part of the lessons, we have learned how to find the equation of a tangent plane. And there was a reason I put down that final formula about the tangent plane so that you can just quickly find it. And so, yes, fx here of the function is going to be y squared, and fy of the function is going to be 2xy. Okay, and so right from that, we're looking at fx at 1, 1, because we now want to find the tangent plane at 1, 1. And so I'm going to substitute 1, 1 into our fx right here. So that gives me 1, and then fy at 1, 1 gives me 2. Okay, and then the function's value at 1, 1. Okay, the function value at 1, 1 is simply 1 times 1 all squared, which is 1. Easy enough. All right, and so now I can easily come up with the tangent plane. So the tangent plane here, we're looking at z equals, so right from that formula we've learned earlier, z equals 1 times x minus 1, okay, plus 2 times that value is 2 times y minus 1. Okay, and then plus 1. That is the equation of my tangent plane. And then I can, in my next step, but I don't want to write as a next step, so right here the z, instead of calling that z, I'm calling that it's my function, my linear function L of x, y. Ladies and gentlemen, that's what the L is all about. Okay, so this is my linear function. And so now, let me erase some space right here. All the work to arrive at this linear function can be now erased, and I'm going to rewrite the equation of my tangent planes right here as a function of two variables. X minus 1 plus 2 times y minus 1 plus 1. All right, and so now once upon having the linear equation, the linear function that represents the tangent plane right here at 1, 1, and again recall for yourself 1, 1 is near this point right here, okay, 1.01, 1.05, and so in that way I am going to say, hey, the actual value for f at 1.01, 1.05, this actual value, instead of doing the direct computation, that can be approximate it by substituting 1.01 and 1.05 into our function L. So we use L, the tangent plane, as a way to approximate, and the value will come out close enough. Okay, so that means now proceeding further into this computation, it's going to give me, so equals, so now I'm looking at 1.01 minus 1, okay, plus 2 times 1.05 minus 1. Okay, so that's making it a lot easier, adding, subtracting, adding and subtracting and multiplication, okay, and plus 1. How easy is that? Okay, so now I can even do this without a calculator. This is going to be a 0.01, right, plus, and then that's a 0.05 times 2, so it's going to be a 0.1. Okay, 0.05 times 2 is a 0.1 and plus 1. And so now my final value is 1.11. Okay, 1.11. So ladies and gentlemen, what I'm saying here, my point is saying is that this value, this actual value, f of 1.01 and 1.05 can be approximately equal to 1.11. But that's only an approximate value right there. Right? It's only an approximate value. All right. And so now let me bring in my actual calculator to show how close we've had, how close we have made in terms of the approximation value and compared to the actual value. And I never bother doing the actual calculation yet, and I want to do it right now on the computer screen. Okay. All right. So right now I'm on my calculator, my TI 8384 calculator, and this is a calculator that's good enough for the kind of work we're doing here. So the actual function value in parentheses 1.01, that's for x, and I mean 01. That's for x, times, and I don't need multiplication, or I can just put it in parentheses 1.05, that's for y, but we need to raise that to the power 2 right here. Okay, and then now, so I'm about to make the calculator give me the actual value. The actual value is 1.11, 1.113525. And what we have here, what we approximated was 1.11. All right, and you can now see how effective and how efficient it was, how effective it was to use the method of linear approximation. Okay. Now there are separate studies about what can we do, how near we can choose a point. What's a good point to choose to minimize the amount of errors? Because see, this is only 1.11, but the actual answer you have seen on the calculator screen was a 1.113525. Okay, and so there's always an error. It's the way how doing approximation is. Okay, and so there are separate studies out there to show you how, or sort of like a good planning of how you can plan to choose a point to make the best approximation. Okay,